So I've got 11 o'clock here on the East Coast. We're going to go ahead and get started. Again, welcome folks. Thanks for joining us again this week for our Best Practices webinar series. We've got a great topic for you all today, wide Wi-Fi channels, high modulation rates, and what it takes to go fast. And I've got two smart people that are joining us today. Mike Graham, who's a sales engineer here at 7Signal, and also Dave Hallis, who's also a solutions engineer for us in CWNA, chaired a lot of IEEE groups as well, so we're lucky to have him. Before we get going today, I got a couple of housekeeping items. For those of you who haven't joined us before for these webinars, I just go through a couple slides of about 7Signal, then we go ahead and get into the content. So I don't take up too much time, but if you're looking for a product tour, you're in the wrong place. From 7Signal, we don't do product tours on these Wednesday webinars. These are all education focused. We want to get you all better with Wi-Fi and teach you some new terminology, teach you ways to find and fix issues without our software. In some cases like today, just give you some best practices, hints, tips, and tricks to get rolling. So there's a couple things that I want to tell you about. If you haven't done an IDC ROI report with us, I'm going to drop this link into chat. You can go to wirelessmonitoringroi.com. That's something that IDC did for us. You can go ahead and take a look at what downtime is going to cost you with your Wi-Fi, disruption with your devices, that sort of thing. And if you want a product tour, you can go to go.7signal.com/tour. If you want access to an archived webinar, you can go to YouTube. Our YouTube channel's got hundreds of webinars that we've done throughout the years here at 7Signal. And if you're looking for CWNP credits, you're in the right place. All of our webinars are certified by CWNP, so you can get continuing education credits from there as well. So a little bit about 7Signal. We were started back in 2007, and we've hit a lot of major milestones along the way. We're now crunching over 1 billion data points on a daily basis. We're on a lot of networks, we're on a lot of devices, and we crunch a lot of numbers for our customers and making sure that their wireless network and their ecosystem stays connected and stays strong. We've got over 200 customers around the world, over 30 partners. I know a lot of them are on board with us today. I mentioned that folks from the EU and UK and Russia were on board. A lot of those folks are partners that continue to log in with us week to week. We've got over 15 patents, and we continue to expand there. And also, we are certified in over 40 countries, including the EU, where we're GDPR compliant. So not only do we stay up to date with our technology and our patents, but we know that privacy is important to you, and we keep that top of mind as we develop new technologies. But we're really all here because everything in the world of Wi-Fi hinders on the digital experience and that end user. So we never lose sight of that here at 7Signal. So whether that's accessing things like email and documentation, applications that are critical to the day-to-day operation of your businesses, or if you're in a hospital environment or an academic environment where you're connecting to different systems that either are saving lives or educating, a lot of that wireless connectivity is dependent on the network, obviously, and the devices that they're on. So here at 7Signal, we're monitoring that end user experience, where really that last hop is the most important to that digital experience. So there's a lot of pain areas that roll into critical Wi-Fi, and what happens if you don't have 7Signal within your organization. You're being reactive when troubleshooting tickets coming in versus having visibility into that wireless network and into those endpoints. You're spending too much time figuring out what's going on with those devices or networks. There's finger pointing back and forth, and this is something that we hear constantly when we go through the sales cycle here at 7Signal, is that folks are blaming the Wi-Fi, or they're blaming the devices or the applications. We get you that data that you need to get right to the problem. So there's no finger pointing, bringing folks back together as a team. So less time getting to the issue, and giving you better insights. Right now, if you're using that kind of what we call the inside out approach, you're getting different insights than you would from the outside in, and I'll explain that in a minute. But you have limitations as far as what your service providers can provide from an SLA standpoint, and you don't have a plan forward. And ultimately, that impacts either your customers, your employees, your patients, your students. It all has a ripple effect. So, and really 7Signal completes the picture. So I mentioned the outside-in approach, and a lot of you have these vendors now. Cisco's in your environment. They're worried about your controllers or your access points. You've got Riverbed in there. You've got Abneta that's worried about your applications, or SolarWinds doing some monitoring. They all have the same approach. They're monitoring your infrastructure from the inside out. They're not understanding what's going on with the digital experience of your end users from the outside in, which is where 7Signal lives, with our sensors and with our agents that live on the devices, any Android, Linux, Windows, Mac OS operating systems, which is where we play. So monitoring that network from the outside in. And often we're compared to application performance monitoring tools. And if you're looking at this, and I know our Wi-Fi engineers are familiar with the OSI model, but it really takes a layered approach to visibility and all the different trouble areas. But you can see where the APM vendors stop. So they stop at that network or the layer 3 module, where 7Signal can flow through the entire OSI model and really give you visibility into where those trouble issues are on your network or on those devices. So with that said, we're going to get on with the show. I'm going to hand the controls off to Mr. Graham, and he's going to lead us in today's presentation. We don't have a trivia question for you all today, but we do have a ton of content to get through. So with that said, Mr. Graham, the controls are yours. And for those of you who have questions throughout, go ahead and use the Q&A pane for any questions that you do have. Dave House is going to be monitoring those as we go. So we'll either bring those up at the end, or if they're relevant to the slide that we're on, we'll talk through those at that time. So Mr. Graham, the floor is yours, and I'm seeing your screen.
Thanks, Don. I appreciate that. And thanks, Dave, for joining me today. You know, with Wi-Fi 6E, 802.11ax on 6 gigahertz, you know, suddenly it becomes, I think, practical to start talking about, you know, really big throughput numbers for Wi-Fi, and wanted to touch on kind of what those are and a little bit of how to get there. So let's begin. Well, this screen is kind of the bottom of the Ofdm 802.11ax modulation rate, data rate table, lifted from mcsindex.com. If you don't know about it, it's a great resource. It has the table that shows all of the Wi-Fi data rates and how to get there. And I thought that would be a good place to start whenever we wanted to talk about how fast is fast. And if you look down in the lower right corner with the red circle, we can see that on a 160 megahertz channel, 1024 QAM, 5/6 coding, that'll get us all the way up to 9.6 gigabits, not megabits, but gigabits per second over the air. And that should easily put 5 gigabits per second of real TCP throughput available, which I think is really fast. And realize that we're really talking about the AP end here. With that, clients are going to support a bit less, and we'll get to that. And really, we're mostly talking about one client and one access point. Obviously, when you have a building full, it starts to complicate things a little bit. Any thoughts on that, Dave?
I agree with you that 9.6 gigabits per second is really, really fast. So
It
I'm
really
sure that a lot of people are probably thinking along the lines, wait a second, I know I've been looking, I ran speedtest.net and I got like 100 megabits per second or something like that. And so
yeah.
that's a good point. That's a lot slower. But I think that as Mike goes through these slides, we'll be bringing up some of these things that, while yes, the Wi-Fi can go really, really fast, things that you want to look for and things to be concerned about.
Yeah. I actually want to get a couple of 8-stream access points and see how they do in bridge mode. I think that would be a lot of fun.
Yeah.
Now you'll notice on here that this table has different guard intervals on it, and for the rest of the presentation, I've really kind of ignored that just to simplify things a little bit. So we'll be talking about spatial streams, modulation, a little bit about coding, and then the channel width. So moving ahead, if we want to go fast, there are really 3 things that we have to look at. More spatial streams, and those are really straightforward. 2 spatial streams is twice as fast as 1, 3 is 3 times as fast, 4 is 4 times as fast, and so forth. So that's really straightforward, and they really do add that way. Not all environments are going to support a lot of spatial streams. You need a certain amount of multipath in the environment for a lot of spatial streams to work. They're not going to work in vast empty spaces or outdoors very well. But in an office environment or a home environment, multiple spatial streams really do work, and they really do add just that way. The second way to get higher data rates is move to wider channels, and that also works just about as simply as it sounds. 40 meg channels are twice as fast as 20, and 80 are 4 times as fast, and so forth. I know that we've talked on other presentations about wider channels and how those are problematic because we run out of spectrum in 5 gig. With 6 gigahertz opening up and equipment is now shipping for 6 gigahertz, a lot of those concerns are relieved. And in fact, wider channels, I'm saying 2x for every doubling. It's actually a little bit better than twice as fast, but in round numbers, twice as fast. And then finally, we can do what we always have done, and we can use a more complex modulation encoding scheme. So we can move from 16 QAM to 64 and 256 and 1024, and those are going to add throughput as well. I think that really covers sort of the physical layer ways to go fast, but there are some other things that really matter on efficiency that we're not going to talk about on this. And Dave knows a lot more about those, but we're talking about anything that does frame aggregation or block acts or really any way to combine data into a single frame, because the preamble part of a frame is huge and slow, and that's really a major part of why the later protocols are faster. It isn't just that we've got more streams and wider channels and more complex modulation. We've also got a more efficient protocol, but once again, we're not gonna touch on that too much on this. Anything I've missed on this slide, Dave?
Well, I think the things that you're discussing, I'm assuming that most people know this, but in case you're not, that I kind of figured to talk about that when we were looking at that previous slide with the data rates and now into here, that's with Wi-Fi, a lot of times people like to talk about the radio, that data rate for the radio. And we've had some other webinars that talked about this, is that well, what about your actual throughput that a user would see? For instance, if I was doing a file transfer, how long should I expect that to take? And that wireless is different than typically like Ethernet wired, or that's when you're wired, that raw data rate is pretty close to what the user is going to see. But when you're wireless, that is not the case. That you end up having to see, and that's actually, if I go on to my Sound Signal commercial type of thing, when Doug was talking about the different ways that we look at things, we can show you, well, this is what you can kind of see as far as real user throughput versus here's a raw radio data rate. So that one of the questions had to do with, are there any rule of thumbs? The rule of thumb it seems like 802.11 and Wi-Fi has always kind of been able to achieve is that when you look at the raw data rate, if you're doing a something like a FTP or a file transfer, you could kind of get into about half of that. And that's just a rule of thumb. There's a lot of different models, just as Mike had that chart up there with all those numbers and stuff, that if you actually wanted to model it, you'd have to kind of come up with these huge models and say exactly how are you doing this. But if it's a general rule of thumb, it's about half of that.
Yeah, I agree. And with 802.11g, half was almost exactly right most of the time. A 54 meg connection would put you in the mid 20s throughput wise. AC and AX do a little bit better. I still tend to use 2x or half, I guess. The over-the-air data rate is a pretty good estimate for TCP, but the efficiency is improving a little bit, and usually you can do a little better than that, but yeah, I use half as well. So let's kind of step through and say a few words about each of these. There's, I think, not a lot to say about more spatial streams. They're almost unequivocally good. There really are very few cons. I got a few notes in here. If you remember 802.11n, it came out with first protocol with multiple streams, and it supported 4, AC and AX up to 8. And what I found, and it isn't universal, but most 802.11n and 802.11ac access points support 4 spatial streams. There's a handful that support 8 AC access points that support 8, but 4 for the most part. I did a little bit of browsing through some of the manufacturers' websites, and it looks like we're probably going to end up with kind of the premium enterprise APs are mostly going to support 8 streams. I think it's what it looks like most of the manufacturers are coming out with. And I did a quick check on Newegg. No special reason for Newegg. It was just a link that I had handy. And I checked on the 802.11ax client adapters that they're selling, and all of them support 2 spatial streams. I didn't find any that supported 1 or 3 or 4. They all supported 2. I'm definitely not going to say that there are no others, but I actually think that's pretty good. There were a lot of 802.11n and 802.11ac client adapters that are single stream, and they are usually pretty bad. And those 2 spatial streams at 160 megahertz wide channels support 2.4 gigabit over-the-air modulation, so they're easily capable of gigabit TCP throughput. What do you think, Dave? How do you like those porcupine APs?
Yeah, I do like all the antennas. The sticking out. Well, that's a guarantee so that birds don't land on there. It's outdoors. So now I think the other kind of thing is, Mike kind of mentioned that chart when we kind of started, that was for 8 spatial streams. And now we kind of mentioned, hey, looked at it, that's the clients, most, everything kind of seen out there, they're just kind of following along the lines of AC and 11N, that there's 2 spatial streams. You'll see that there's, maybe there's other clients that might support 3. If you do come across something, some client card that supports 8, let us know. We'd be interested in knowing about that. It's always kind of interesting to see the number of streams that a client card can. But so this is kind of the part of the things that I think would be very useful to people is when you're looking at it, there is a big difference between 2 and 3 spatial streams. So, if you end up getting something that's even more than that, obviously you're going to see that boost in throughput. There are also some things that have to do with the number of antennas that you have. So, how exactly that on the client card that they're going to have all those antennas, it becomes a bit more of a challenge as well. All kind of interesting stuff there.
Yeah, I think so too. And I know the question might come up, if the clients are only supporting 2 spatial streams, then why have access points that support 8? And really the reason there is MU-MIMO. They are going to multiplex up to 4 clients onto a single transmission. So it's, that was a big push for AX, really was efficiency. And having a lot of spatial streams on the access points enables you to support more clients using MU-MIMO. And I think that's really the reason. I did say that there's really no downside to spatial streams, more spatial streams. There are a couple. One of them is cost. Obviously, the more spatial streams the radio card is going to support, it's going to be more costly. And the other is that it's going to use more power. And an access point, it may not matter until you start to exceed the power over Ethernet capabilities. In a client, that can matter a lot. If it's a battery-powered device, a handheld device, running those extra spatial streams is battery and power intensive. So I think that's one of the reasons we don't see a lot of clients with a lot of spatial streams. I lifted this chart from Broadcom's website, and I think everybody's probably seen this one. This shows the breakdown of 20, 40, 80, and 160 megahertz channels in 5 gig and in 6 gig. And usually, at least before the 6 gig part was added, we would use this to show, there's only 260 megahertz channels, and there are only 6 80 megahertz channels. So it becomes challenging in an enterprise environment to use those wide channels without the access points stepping all over each other. And so mostly in enterprise environments, we see 20 and 40 meg channels used in 5 gigahertz. 6 gigahertz changes things a little bit. Suddenly we have 7 channels in 160 megahertz and 14 and 80. I don't think that in big open environments, 160 is still going to be super practical. I think it will be in smaller environments, smaller buildings where you have a little less channel reuse, and environments where you have a lot more walls rather than big open environments. But at 14 channels, 80 megahertz, I think that's going to be very commonly used in 6 gigahertz. I really do, with probably 40s and 20s being reserved for maybe things like sporting arenas where you've got a lot of access points and you're essentially in a big open room. What do you think, Dave? Does that sound on point, or you think I missed that?
I think you're right on point. Part that we should probably talk about a little bit is, since we do these webinars and some of them they kind of get into, well, hey, those 160 megahertz wide channels, you don't want to use those. Well, it really kind of depends. So with 7 Signal, when we're talking about most of our customers, we're not talking about somebody that has one access point at home. They got like a couple client cards. No, we're talking about enterprise users. We're talking about arenas. And so therefore, in those use cases, we want to go to the smaller channels. But that's not really the question about this webinar. This webinar is more about, well, if you really did want to max it out, what can you do? So if you're at home and you've got a lot of space between your neighbors, then if you've only got like one access point, or maybe you've got a couple, but if once you go to 6 gigahertz, therefore that there's actually more 160 megahertz wide channels. So therefore, hey, you actually can go and run it. And when you want to max it out, how far can you go? So in the home, because a lot of times people will say, well, I know I could run blah blah at this really huge throughput. Well, exactly how did you get there? Are you at home with one access point? Yeah, you can max that out. Carpeted office, yeah. We kind of admit that that's maybe not something that you'd want to do. And that's actually kind of like what Mike was saying as well. So therefore, but if you did want to max it out, yeah, go to 106 megahertz wide channels.
Yeah, and I do think, like I said, that with 6 gigahertz and not in big environments, but even in smaller offices, medium-sized offices, those big channels will be practical. I mean, we used to make do with 3 channels and 2.4, and it made the networks work. So not an impossibility, I think. Moving on from spatial streams, talk a little bit about wider channels. And I know kind of at first glance, it sounds like, the panacea, everything moves to wider channels and it just goes faster. There are some downsides to that. The first one of those is thermal noise, and that is the noise that the receiver generates internally. Just the atoms and the electrons bumping together is going to cause a certain amount of noise, and it's well characterized. Negative 174 dBm per hertz at room temperature, and I think room temperature in this case is 300 Kelvin or about 80 Fahrenheit. Oh, it put it in the chart, 80 Fahrenheit or 27 Celsius. So room warm temperature. You add that up over a 20 megahertz channel and negative 101 dBm. So not a whole lot of noise on a 20 megahertz channel, but as you start doubling those channels and doubling the noise that they're going to hear, it begins to add up. And at 160 megahertz, you're looking at negative 92 dBm of noise purely internal to the radio, not counting anything external. So you're already starting behind a little bit. Also, and there's really no escaping that. That's just sort of the way the world works. And all the other noise, anything external, the lightning and other radios and cosmic radiation, all of that doubles as well. It isn't on 5 and 6 gigahertz. There isn't a lot of that. But yeah, you're going to double that up, and if there's other radios nearby, you're going to double up the noise you hear from those as well. And just since I put down there's no escaping it, I actually went and found a picture, this kind of plumber's nightmare over here in the lower right. I lifted that from a NASA website. It's part of a receiver on their deep space network that they use to communicate with Voyager and those other outer solar system probes. And they actually cool the front end of that radio receiver to just a few degrees above absolute zero with liquid helium to reduce that noise, to help pick out those very weak signals from the probes from deep space. And I kind of thought that was kind of super cool, so I stuck a picture of that in there. So we'll come back and see if there's any questions on this. I think it's kind of an interesting subject. Any thoughts on that one, Dave?
I really like your slides, Mike, especially like this one and these, some of these ones around here, because a lot of times people just kind of like say, well, all things being equal, so do you just divide it up? It's like, oh, okay, so instead of 40, you're doing 20. No, there's actually, it's kind of two things to keep in mind. As you kind of go to the narrower channel, then the noise floor is going to be lower. And as you go to a wider channel, that yes, things do work. You can get these data rates, but you have to kind of keep these things in mind. That that since that noise floor is starting to come up on you, and also we're talking about where exactly are you? Are you out in the field off on your own, or do you have neighbors next to you? That's going to make a big difference. That if you are in a carpeted office and there's somebody right next to you in the same building, that's going to raise your noise floor. And so therefore, those are the types of things that, why you might not achieve these types of throughputs. But I definitely like this slide here, kind of showing you that, yes, you can achieve it, but keep in mind that, basically your ranges are going to come down because of this.
Yeah, and like you mentioned, it isn't just that internal thermal noise that doubles up every time. It's all the other, your neighbors and stuff, you're hearing twice as many of those when you double your channel as well, and so you've got twice as much noise. Not overwhelming, but you are walking uphill. The third thing that we talked about was using more complex modulation, using denser coding rates, and really the key thing that you need to be able to decode those higher rates is a certain signal to noise ratio. I did a little bit of research and actually lifted this table from I think it was from a Comcast technical paper, but I checked it against several other sources, and it varies by about 3 dB, but nobody seems to vary on an exact pattern. So I think these numbers for SNR are really close. Something that I do want to mention here, since I think maybe a lot of people don't really understand the code rate column, they maybe understand the modulation and how we're using a more complex symbol that carries more bits in each symbol with the higher modulation rates. But I don't think the coding rate is very well explained in most documentation. And it's really pretty straightforward. It's how many bits of data are included in a code string. So for 1/2, that's half actually. It means that half of the bits that you're transmitting are actual data. The other half are part of an error correction algorithm. So those that use low coding rates are very robust. They can withstand a lot of errors, and you can still decode those packets, those symbols. As you move up to 3/4 and 5/6, that means 3 out of 4 or 5 out of 6 bits in your stream are actually data. So there's very little error correction built in, and it makes those links a little bit more brittle whenever you're using those really high code rates, and they therefore require a little more SNR, as well as, of course, the modulation rate. As you move to more and more complex modulation rates, you need more SNR, you need a cleaner signal. And over on the right, there's a graph which kind of goes in the wrong direction, I think, but it shows that, for MCS0 there in blue on the left, you're going to need 5 dB or a little less to decode that, and it moves across to MCS11, 1024 QAM, where you're going to need, neighborhood of 34, 35 SNR to be able to decode those packets. And that's, like I said, the data tables don't match up exactly. And I found a lot of data tables. Most of them are really close, 3 or 4 dB off from each other, but not generally in a pattern. So I think this is probably really accurate. Anything to say about complex modulation coding, Dave?
Well, I do. There's another table that I really liked was this SNR table. That because one of the things that you might hear is, oh, these higher data rates, you can't really achieve them. It's like, well, actually, you can. It kind of depends on what's your use case. That, you know, does your access points in the basement on the far end of the house and you're on the other side of the house, or is your access point at home like in your office and you happen to be in the office as well? There's a conference room and the access point is in the conference room and there's some people that are in the conference room. In those cases, that yes, you could get that SNR. Now, I would agree, though, that if it's the other case of you're in a carpeted office and you're in a conference room and the access point is outside of the conference room, then you know you're probably not going to be able to meet that SNR. But this does kind of show that these is it possible? Yes, you can achieve some of these higher data rates, really high data rates.
30-something SNR is not unreasonable at all. Very achievable. Even walking uphill against the noise on a wider channel, those are entirely achievable, I think. So I'm going to bring it all together here a little bit. I'm going to take our SNR column and going to take our noise column from the others and add them all together. And we're still on this table talking about a perfect radio that has, you know, no other internal noise beyond the thermal noise that you can't avoid. And that's not really real. So I went down and I added 3 dB of noise into things to kind of make it a little bit realistic. And I did this without checking any of the manufacturer's tables. And then whenever I finished, I looked up one of Cisco's access points, the 9130, and checked that bottom column, the 1024 QAM 5.6, 160 megahertz, and sure enough, my table matched theirs, and I was very relieved that my math was correct. So I've circled a couple of values here. The first one up on the upper left one, 256 QAM, 20 or 40 megahertz channels, basically what we're used to up until very recently. And you'll need upper neg 60s, neg 70 to decode those. And for those where most people are doing, I think, negative 65 dBm surveys. So that matches up pretty well with that. If we move to AX and we start looking at 1024 QAM and we start looking at 80 and 160 megahertz channels, those numbers get a lot bigger. Instead of upper neg 60s, we're looking at mid to upper neg 50s. So, let's call it 10 dB more signal. And that's a lot more signal. It's definitely achievable. There's no reason that you can't get into the mid neg 50s at all, but you're not going to do it through very many walls. What do you think, Dave?
Well, I think you hit on a really good point about site surveys. And all you have to do is kind of look at that bottom line there, is that, if the target is minus 65, then yeah, you're not, even all things being equal, you're not going to really reach those higher rates there. So that would be something else to kind of think about as far as deployments. But you'll still be, running with very high data rates. So I like this slide as well, kind of bringing everything together.
Yeah, we don't want very high data rates. We want to go fast. All right, next slide. I actually pulled, I went and found a customer that had a couple of access points in the same room with the same Sapphire Eyes, our sensor. And one thing that it does whenever it's doing its throughput test is it records the over-the-air data rates. So I found 2 access points off of the same sensor in a big room and about 10 dB apart, since that's sort of the order of magnitude that we're looking at. The one in red here at negative 53 dBm, and you know that brings us easily up to here, and it might be the sort of number that you might survey for a 160 megahertz 1024 QAM network. So we're in the ballpark for that. Unfortunately, this was just a 20 megahertz wide site, but I think it'll serve the purpose. And we can see that basically in red here, you know, over 90% of the traffic is going at the highest modulation rate. Once again, AC, not AX, and so forth. But as we would expect, it's slammed up against as fast as it'll go. But if we back off just 10 dB, 9 dB, and we're still better than a negative 65 survey, look in yellow what happens to the actual data rates. And this is averaged over a week. So, you know, this is a really good long-term average here. We can see that, you know, instead of being up at MCS 9 all the time, suddenly we're down at, what is that, MCS 5 most of the time. Some of the packets are a little better, but there's a big fall off. Even whenever we're at the, you know, better than negative 65 that a lot of people survey for, isn't enough to really max out the radios. So I wanted to put this in here to speak to, you know, that you really do, if we're going to do these 1024 QAM networks and we're going to do them on wide channels, even looking at older technology, it's clear that we're going to have to have a lot of signal. What do you think, Dave?
I agree. This kind of does a good job of highlighting that the you know, these, it's not something that's unachievable, that you can actually reach some of these data rates with these types of signal strength and SNRs.
Yeah, but you don't have to fall off much before you're not there.
Yeah.
And as I said, these were in the same room, so it's very much an identical environment. Kind of hitting our wrap-up slide here, and if you remember back on the first slide, we kind of said that fast was 2 gigs. So I wanted to go back and look at, well, what does it actually take to get to that 2 gig number? And spatial streams, that's easy. 2 is the best we're going to do with most client adapters. There may be some 3, there may be some 4. If you're building a machine that's got to have really high Wi-Fi throughput, maybe you want to find an access point radio card and put it in there, and instead of really a client card. But basically, 2 is as good as we're going to do. If we look at channel width, 80 megahertz tops out at, I think it's 1201 megabits per second, 1.2 gigabits per second on 2 streams. So that pushes us to 160 megahertz if we want to hit that 2 gig over the air. And then even with 2 streams, 160 megahertz channels, we're still going to need MCS 10 or 11 to hit that 2 gigabit number. If we fall down to MCS 9, I don't have the table in front of me, but that does not do it. So if we look back to our table and we remember no external interference was figured in, so we're completely clear channel, everything's working right, the wind's at your back, you're going to need somewhere in the neighborhood of -58 if you want to achieve that 2 gigabit over the air. And you know, truly that's an arbitrary number. I picked it really because I figured fast is more than a gigabit of real throughput, user layer throughput, and that's going to take 2 gig over the air, or pretty close to it. So somewhat arbitrary, but that's how I got that 2 gig number. And then everything else just sort of falls out from that. And I hope you'll forgive me for walking you through all of those slides to get to what is essentially the receive sensitivity table that every manufacturer publishes. But I hope it's a little more understandable now. And I think that does it. Dave, did we get any questions?
We did. Hey, Dan, how much time do we have for Q&A?
Yeah, we're right on time here, so which is, you know, toward the end of the broadcast, so we've probably got time for 1 or 2 questions, Dave.
Okay, good. There was one which I think is very pertinent, and Forrest kind of put this in here. I'll read this out because that are there charts for recommended modulations at all for choose based on factory with many machines, library, warehouse, dense cardboard products, warehouses with all metal parts, fairgrounds, downtown, etc. Do you actually select those modulation schemes? I don't recall seeing anything about the ubiquity router. This presentation that Mike was kind of going on about, it's really more about the peak. And the things that we kind of mentioned throughout is that those peaks will really be, to achieve them, there's like some things that you'd want to keep in mind. It's really that, you know, if, say for instance, you're doing some gaming at home. You're gaming at home, sure, you know, you've got one access point, so you can kind of get that. We were talking about the you know, like the signal strength, if you're using wider channels. Some of our other webinars, we kind of mentioned not doing the wider channels, just so that you, because in a carpeted office, you would need those channels. So would that really apply to things like a factory automation type of thing? That's where, you know, you're really not going to kind of go off with those types of channels. So I don't know if any guides for those, but that you could definitely see that with this chart, that we're kind of focusing on it from a perspective of getting like the highest throughput. You could also kind of look at it from the other perspective and say, okay, I'm really more interested in, you know, what is my actual throughput. The other thing to keep in mind, as Mike has kind of mentioned, you know, trying to get up to like a gigabit of throughput. You know, where exactly is your traffic going? You know, is your traffic going out to the internet? And you know, what does that pipe look like? Is that a gigabit? At my house, I don't have a gigabit at my house, so that's definitely, there's some limitations that come in from other places that are imposed.
Yeah, I don't have a gigabit either, Dave. But yeah, I think on the difficult environments, we'll just kind of lump it all together. You really want to be looking at the other end of the chart. You know, you don't want to walk uphill against more interference. You know, so that's going to push you to narrower channels instead of wider channels. You know, fortunately, in a lot of those difficult environments, they're usually not very user dense. So something like a warehouse may very well have many more access points than it has users. So in that case, you don't have nearly as much worry about interfering with yourself, because yeah, there's a lot of access points, but there's not a lot of traffic on most of them. So you really start looking at the other end of the table and look, you know, not at kind of how fast can I go, and you know, maybe I want to support a VR headset, or you know, maybe I want to stream high resolution video over a Wi-Fi link or something like that. You really are usually looking at the other end of the table, where I want to send the user a location to go to and a product to get, and he's going to scan a barcode, and that's what's going to come back. Where, for the most part, those applications, there's always exceptions, but those are generally lower throughput applications, and usually you're going to want to look at making it very robust rather than very fast. So lower channel widths, lower modulation rates, lower coding rates. And I'm not suggesting you turn off the higher rates. Use it if you can achieve it, but you should really probably design around lower performance system, where performance means throughput, lower performance, higher reliability. Do we have time for another one, guys? Or?
Well, I was just going to agree with you, Mike, that I think that the guidance that I would give is take a look at your use case. Kind of like the question about the factory automation. Factory automation is like, well, what exactly are you using that for? What type of throughput do you actually need for it? As Mike, you just kind of mentioned, yeah, I know that these barcode scanners, it's like, if you get like a megabit, that's plenty sufficient for what you're using. And so you don't really need, like, it could be really what you need is the stability. Now, in your factory automation, maybe what you're doing is you've got something that's rolling past you and you need to do a software update of some component. And so therefore you might need like a tremendous amount of throughput. So in that case, maybe it does make sense for you to run maybe something like a much wider channel than normal. But my general guidance is look at your use case for these types of, especially manufacturing and so forth, and then figure out where exactly you want to be, with your channel widths and so forth.
Yeah, and I kind of know where that one came from, Dave, because we do have a customer that updates software and devices over wireless as they're being packaged up and tested and packaged. And our recommendation there was, for that area of the warehouse, yeah, it gets big fat channels, and it gets those channels reserved so they're not anywhere else. And really the rest of the warehouse gets a much milder system. So with a little bit of planning, you can have both.
Yeah. There were some questions about multi-user MIMO. I think that there's also, we talked a little bit about this, as AX is for the high efficiency, and so that gets into the multi-user MIMO, the OFDMA. I think that's quite a big topic. So that's why I kind of went past those. I
thought about talking about OFDMA a little bit, and I decided that was just too big a topic, and maybe we'll give it its own webinar.
Yeah, that's what I was thinking. That deserves its own webinar.
Yeah,
I'll let you do it, Mike.
Yeah, you get Mike to do that. No, actually, I think Jim Vada did one on OFDMA a couple months back, but maybe it could use an update. So I'll look at that and get it on our radar. But we went a little bit over today. Awesome presentation, Mike. Dave, thanks for adding color along the way and taking questions. I did see some questions come through about getting a copy of today's recording. That is available on YouTube. Everyone who registered for today's conference will get a link sent to them to the YouTube channel with the direct link for this presentation today. Thank you all so much for coming. We really appreciate your time that you give us every week, every Wednesday at 11 Eastern.